Thank you very much. We are in for a treat now with the first lecture to be presented by Yael, Tauman, Kalai. She is a cryptographer and theoretical computer scientist and senior principal researcher at Microsoft Research in New England, as well as an adjunct professor at MIT. Of course, she received a prize, the ACM Prize in Computing 2022, and I read from the citation, for breakthroughs on verifiable delegation of computation and fundamental contributions to cryptography. Yael, the stage is yours.
Thank you so much. Hi, so good to be here. I guess I'm waiting for the presentation. Oh, here you go. Okay, so wonderful. So thank you so much. Thank you so much for inviting me, and thank you so much for showing up. It's a great privilege speaking in front of all of you. By the way, since I gave you guys my bio, my affiliation slightly changed. Now I'm full-time at MIT. I retired from Microsoft just the beginning of September. Okay, with that, what I want to tell you about today is about compressing proofs using cryptography. So what is this about? By the way, the clock says 30 minutes, but I believe it's an hour presentation? 45 minutes. Okay, fantastic. Okay, so what is this about? You know, proofs are very, very long. Most of you write proofs. You know how difficult it is to write proofs and to verify proofs. So what I want to tell you about today is how to make proofs much shorter and much more easy to verify. Now, this should look like magic. And the reason I'm saying magic, because it looks like impossible. You know, when you see magic, it's like, that can't be. And that's what your kind of intuition should be. How can you just take a proof and compress it? And let me actually prove to you that this is impossible. So, more precisely, what is my goal? My goal is to take a long proof and automatically compress it and make it shorter and much more easy to verify. Okay. Why is this impossible? You should be known, there's no way to do that. And let me actually show you why you should think it's impossible. So take, the class in computer science of NP, all the instances that have a polynomial size proof. Now, if you could take this polynomial size proof and just shrink it, let's make it log size proofs. Now you can just enumerate overall proofs, and you would get that NP is equal to P. Now, we all believe this is impossible, right? Okay. So, nevertheless, I'm going to show you today how to compress proof, and I'm going to use the magic of cryptography. And really, I'm a cryptographer. It's a really magical field. I see with Diffie here, who kind of invented much of this magic. And I'm going to use this magic to compress proofs. Now, just jumping ahead, let me tell you, I'm not going to compress it up to log n, where you can enumerate, but I am going to compress it into very short proofs. So before I tell you how we do that, let me just a little bit tell you why this is such an important topic today in particular, not just mathematical curiosity, but actually today a lot of our work are done not on our own devices, on some cloud platform, or with, now there's kind of the popularity of blockchain technology, and now even in the blockchain, even to verify a single transaction is a huge computational burden. So these proofs are actually now used in particular by various blockchain technology like Ethereum and others. And so it really is of practical interest as well, beyond just academic curiosity. So with that, let me be a little more precise about what I'm going to show you today. What's the goal? So my goal is to take any instance X, you can think of it as a theorem, and any proof W, and we call it a witness for the instance. So I'm going to take an instance X and a witness or proof W, long proof, and my goal is to compress it to a small kind of certificate that certifies that the correctness of X, okay, that X has a witness. And more precisely, what are my two properties that I want to be satisfied? So the first is what's called completeness. It says that if W is indeed a valid witness, or if it's in some corresponding relation R, if it is a valid witness, then the certificate, I can generate a valid certificate of size much shorter than W. I can generate it in polynomial time, so efficiently. And the time to verify this succinct certificate is very short, much less than the time it takes to verify the witness. Okay, so this is just completeness. The more subtle requirement is what's called soundness, which loosely speaking says you cannot fake a certificate for a raw false claim. So it says for every X that's false, that's not in the language, it should be impossible to generate a valid certificate. Now, we can't get quite this. We're going to slightly tweak this condition, and what we're going to argue is that it's not impossible, but practically impossible. Now, what do I mean by practically impossible? And this is where, by the way, this is exactly, the practical is where kind of the crypto comes in. So, you know, when I talk about proofs and succinct proof, what does that have to do with cryptography? You know, proofs are studied by mathematicians. It's about, you know, there's proof complexity or proof theory. It's a big field in mathematics. So why are cryptographers studying this? And what's cryptographic about it at all? So this practically is where crypto comes in. So what I'm going to argue is I'm not going to be able to say that short certificates for false proofs do not exist. I can't say that. What I can say is that they're really, really hard to find. And what I mean by hard to find, I say, well, if there exists some adversary that manages to create such a fake proof for a false statement, then it means that this adversary must have been able to break my underlying cryptographic assumption. So I'm going to somehow embed a cryptographic assumption. For example, hardness of factoring. That's one of kind of our, you know, that given 2 primes, P, the multiplication of 2 primes P and Q, if I give you P times Q, it should be hard for you to find P and Q. It's hard to factor. That is just an example of one of our cryptographic assumptions. So this is the guarantee I want, that if an adversary manages to fake a proof, then he must have been able to solve my underlying cryptographic assumption, or he must have been able to factor large numbers. Okay? Okay, so this kind of soundness is what we call computational soundness, because it's only against computationally bounded adversaries. If the adversary is all-powerful, he can always break our cryptographic assumptions. If you have all the time in the world, you can factor large numbers. But we assume that our adversaries are polynomial time, are efficient in some sense. Okay, and so I said the cryptographic assumption, but where's this cryptographic assumption? Where is it hiding? Like how does this have to do with the cryptographic assumption? So we assume that there's some common random string that both the prover and the verifier share, and it's used to generate the proof and to verify the proof. And in this random string, that's where we embed our assumption. Now, if you think about, if you may be like, wait, where's this random string coming from? What is this random string? So, for example, in what I'm going to show you today, this random string is just a description of a hash function. So it's something that's common. It's easy to generate. It's not like out of the blue kind of thing. But for now, just think of it as just a random string that both prover and verifier know. And this, such a certificate system, such a succinct proof system, is what we call in cryptography a succinct, non-interactive, because it's one shot, and the idea of non-interactive will be clear why we're emphasizing this in a minute. Succinct, non-interactive argument. We call it argument. Argument is another word for computational proof. We can't really use the word proof because it's not a proof. A proof is a statistical thing that you cannot generate. There's no proofs for false statement. This is kind of a computational version, and so kind of a relaxed name for that we came up with is argument. Okay, so succinct non-interactive argument, or SNARGs for short. That's kind of the jargon for that. Okay, so what I'm going to tell you today is how to construct such SNARGs. And we're going to begin with kind of a very brief journey of how we came about these constructions. And I think this journey is just a historical journey that's, I think, really, really beautiful. So I want to share that with you. I'll go over it kind of fast, but let's see how it goes. Okay, so this started with the notion of zero knowledge proofs. So what are zero knowledge proofs? It's not at all about succinctness, invented by Goldwasser, Mikali, and Rakov. And their goal was to come up with proofs that reveal no information about why the statement is true. Okay, they want to convince you, but do not want to reveal information. And what they noticed quickly is that it's impossible to come up with zero knowledge proofs. And let me just tell you, cryptography, that's what, it's all about, everything is impossible, actually. Nothing is possible in cryptography. And it's really kind of an art of overcoming these impossibility results. And so how do they, and the reason this is impossible is if you think about it, take a proof. You can't say it has no information. Of course it has some information. Like, for example, it may be worth money. If I have a proof of some really important open problem, I can sell it. It's something. There's information in there, no matter how much I try to obfuscate the proof. In order to overcome this impossibility result, what they did is they changed the model. And this is often what we do in cryptography to overcome these impossibility results. We kind of change the way we think about things. And they completely changed about how we think of proofs. So we've been studying proofs for thousands of years, starting in ancient Greece, by Euclid and others. And now from the mid-'80s, the way we think about proofs has changed. And the way they thought about proofs, in order to overcome in order to be able to achieve zero knowledge, is they considered what's called interactive proofs. In an interactive proof, it's an interactive process between a prover and a verifier. Moreover, the verifier uses randomness. It actually kind of tosses coins as it converses with the prover. And the guarantees are slightly weaker than the guarantees of classical proofs, in that now there's some probability over them. So the claim is, the goal is, or the guarantee is, if X is in the language, the verifier will verify will accept, equals 1 meaning accept. So this is a bit of notation. But the idea is, if X is in the language, the verifier will accept, it will output 1 with very, very high probability, okay? Let's say 0.99. And if it's not in the language, he will accept with very small probability, say 0.01. And these are just arbitrary. By repeating, you can get these probabilities as close to 1 and 0 as you wish. So basically the point is, yeah, it's like classical proofs, but there's a tiny probability of error. And you can make this tiny probability of error exponentially small. Okay, so using this interactive proof model, later they were able to show, Goldreich, Mikali, and Wigderson were able to show that actually they can convert any statement, any claim, any witness, any proof into a zero knowledge proof. So that's remarkable. I can take any proof and make it zero knowledge in this model. Wow. Okay, but this is not the topic of this talk today. What turned out is that these proofs can be made much more succinct, much shorter, much more efficient to verify. And here's like an example. Take a chess configuration, take a chessboard. Suppose I want to prove to you that the black player has a winning strategy. How do I do that using a classical proof? The only way I can think of doing that is saying, for any move of the white player, there's a move of the black player, such that for any move of the white, it's going to be kind of, like an exponential sized tree. So I don't know how to do that succinctly. But it turns out that using an interactive proof, the verifier can be very efficient. And this is a result by Lund, Fortno, Karloff, and Nissan, and by Shamir. So they started, and Shamir kind of finished the work. So this is only for space. They can't take any proof and make it succinct using interaction, but only the proofs that can be verified by small space, okay? Or languages that can be computed by small space. So that's not for all languages. So only for languages that can be computed by small space, they have these small or succinct interactive proofs. So how do we get, so two things. First, they're interactive. We want snarks non-interactive. And second, there's the space issue that comes in. But later, soon after, the new model of multi-prover interactive proofs were introduced. So it's a different model. It was again inspired by zero knowledge. So whereas the previous result on zero knowledge with interactive proofs, they needed some computational assumption. They assumed one-way functions exist, some cryptographic assumption. They wanted to get away. They didn't want any cryptographic assumptions. And in order to get that, again, it's impossible using an interactive proof, so they needed to change the model. This is, again, kind of a recurring story in cryptography. And what they did, they introduced a new model of proof systems called a multi-prover, or here a two-prover interactive proofs. And here, the verifier is assumed to be talking to two provers, not just to one. So it can send questions to both provers and get answers. And importantly, what gives this model its power is it's assumed that the two provers do not interact. Okay, so think of there's a wall between them. They're in separate rooms, no interaction between the provers. And the reason this is such a powerful model is, think about suspects. So the point is, it's very hard to lie, to cheat, if there's two provers that cannot interact. Because think of like suspects. If you have two suspects that committed a crime, it's easier to catch them because they need to kind of cheat consistently with one another. And that's much harder than just cheating on your own. And this is really what gives this model its power. It was shown that in this model, you can make proofs exponentially shorter. So you can take any proof and really compress it exponentially. More formally, what it was shown, that you can take for any language that has a proof W, a witness W, using this only two provers, you can make the communication, the question size and the answer size of only polylogarithmic length in W. So this is kind of really remarkable. And really, I won't have time, of course, to show you how this is done, but it's really by kind of checking consistency between the cheating provers. It's really how you would think of doing it if you had two suspects that committed a crime. This is really kind of how this proof systems kind of catch cheating provers. Okay, but here's what's really, if you're not blown away yet, I think this will really blow you away. So it was noticed, well, if you can make proofs exponentially shorter, then actually, let's do the following. Have prover one write all possible answers for all questions he can get. There's only logarithmically many questions because we made it exponentially shorter. Have prover two write the answers to each and every possible question he may get. Now, what happened? You can think of all of these answers as one big proof that can be verified by reading kind of only two cells in this proof. This is exactly what's called a probabilistically checkable proof. So a probabilistically checkable proof, this is what it allows you to do. It's a proof that essentially you toss some coins and you read only a few bits of the proof. And by reading only a few bits, you can verify if the claim is correct or not. So this is what's known. This is mind-blowing. I can take any proof, convert it into a probabilistically checkable proof, so that you only need to read 3 bits, 3 bits of the proof. And if the claim is correct, you're going to catch me. I'm going to be able to cheat only with probability 1/8. If 1/8 is too big for you, repeat. Okay, this is mind-blowing. Okay, so I can actually make a proof so efficient to verify. You only need to read 3 bits. However, you need to store this entire PCP somewhere. So in other words, if I tell you, believe me, I have a PCP in my hand, don't worry. What questions you want? If you tell me the questions, and I can adaptively kind of answer, I can cheat. Okay, but if I first give you the PCP without knowing where you're gonna, PCP is short for probabilistically checkable proof. If I first give you this PCP, and then you choose where to read, you'll catch me. But I need to give you the proof. You need to store it somewhere. I don't know, you know? So that's a bit of a question how we do that. And we're gonna show how to do that using cryptography. So far, no cryptography. This is kind of the evolution of proofs. So far, what I showed you, starting from zero knowledge, interactive proofs, multi-interactive proofs, so on, I just kind of showed you kind of the evolution of proofs in computer science, where we start with classical mathematical proofs. This was until the mid-'80s, so thousands of years. Then, all of a sudden, we got the gift of zero knowledge, or interactive proofs, followed by the model of multi-prover interactive proofs, which led to the PCP, or probabilistically checkable proofs. And what I want to do in the remaining of my talk today is to show you how we use this beautiful kind of evolution to construct our SNARGs, our succinct, non-interactive arguments. Okay. And this is where the crypto is going to come in. So far, no crypto. Okay, so let me first show you a succinct yet interactive argument for NP. Okay, not non-interactive yet. It's still going to be an interactive process, but succinct. So I'm going to show you how to take any witness W, which may be long, and convince a verifier that X is in the language, but the verifier is very efficient, and the communication is much, much smaller than the witness W. And here's the basic idea. I'm going to use the PCP. So the prover generates this long PCP. So it takes his witness, he converts it into a probabilistically checkable one, but the PCP actually is even longer than the witness. Okay, so I can't give the verifier the witness. He can't read, he can only read a little bit. So what I'm going to do, I'm going to what's called hash the witness. I'm going to send kind of a digest of the witness, not the entire, so of the PCP. I'm not going to send the entire PCP, that you can't check. I'm going to give you kind of a compressed version of it. So what is this hash function? What is this hash? So essentially what I want from this hash, the properties that I want, is that I can take a long string, it takes a long string, and it squishes it down into kind of a short digest. And importantly, I want it to be binding. I want it to be or computationally binding. I want it to be that once the prover sends this hash, he's stuck. He can't later kind of change his mind about the PCP he put in there. Okay, so it should be kind of binding to him. At that point, he chose the PCP, that's it. He can't change his mind and later, open to different PCPs. And the third thing that I want is that he'll be able to open this hash locally. Namely, when I tell him, I know you hashed a long string, what is the ith bit of the string you hashed? He'll be able to kind of give me some opening that convinces me that the ith bit is what he claimed of this hash. And so assuming you have such a thing for a second, assume you have such a hash, then let's continue our interactive argument, our computationally sound proof. The prover hashes the PCP, so now it's small. The verifier now behaves like a PCP verifier. He chooses which bits to read of the PCP, so he tosses coins, chooses which bits of the PCP to read. So location, let's say I1, I2, I3 of the PCP. He sends these bits that he wants to read to the prover, and the prover tells him, okay, yeah, my PCPs in this location are bits 1, 2, and 3, whatever they are, and he sends an opening. So he tells me, yeah, see, it's consistent with my hash that I sent you in the first message. That's it. And the verifier now verifies as if he's the PCP verifier. So essentially what we did we used cryptography to essentially take this long PCP and kind of squish it in the first message. So think about the first message. We gave the prover kind of a succinct version of this PCP, but committed, like it committed the prover to an actual PCP. And of course, you should ask, wait, does such hash functions exist? And the answer is yes. We have many constructions of such hash functions under standard cryptographic assumptions. Okay, so we know how to construct these hash functions. Merkle tree is one way we know how to do this for those who have heard of it. But there's many ways we know how to do these things. Okay, so far, what we did is we constructed an interactive, succinct protocol. I promised you non-interactive. I promised you a certificate. And what I delivered is this interactive thing. So the last thing I want to do today is show you how to eliminate interaction. Okay, so how to go from an interactive solution to a non-interactive solution. And this, again, is kind of a magical idea, which dates back to Fiat and Shamir. So let me tell you what this Fiat-Shamir heuristic is about. So what they showed, they said the following. Take any interactive protocol, like the one I showed before, or any interactive protocol, where let's think of 3 round for simplicity, 3 messages, where the message of the verifier is just random. Suppose the message of the verifier, here denoted by beta, is a random string. And by the way, in the protocol I showed you before, the Kilian-Mikali protocol, it is the questions from the verifier, you can think of it as random string. Okay, so it is like a random, what we call the public coin protocol, where the verifier just sends kind of random coins. Such protocols where beta is random, Fiat and Shamir proposed the following way of eliminating interaction. Their idea was, have the prover send the entire interaction. So he'll send alpha, he'll compute beta and gamma. But the prover cannot compute beta as he wishes. Then he'll be able to cheat. The restriction is beta needs to be a hash of alpha. Now, again, hash is just a function. Okay, think of it as I'm not saying what properties I need from this hash function, but that was their idea. Their idea is the prover will compute alpha. Beta is restricted to be some function hash of alpha, and then he will compute gamma. And that's it. And the verifier will check that alpha, beta, gamma is accepting, and beta is indeed a hash of the first message. So now, no interaction. That's it. But they need to agree on a hash function. That's my common random string in the sky that I mentioned. That's a description of a hash function. They need to agree which hash function are we going to replace the verifier with. Essentially, instead of having a verifier choose beta, the hash function chooses beta. And now the question is, which hash function do we use? So they need to agree on a hash function, and now no interaction at all. So I can take my argument system, my interactive argument that I showed, where I hash the PCP, verifier sends questions, prover answers. I can, instead of verifier sending the question, the hash function can send the questions. So the questions to the PCP are computed by a hash function. That's your snark for you. That's it. But now, of course, you should ask, well, is it secure? I mean, the verifier chose random coins, really random. Now we're saying, no, not random anymore, a hash function. The coins are defined by a hash function, applied to the first message. Is it secure? Why should that be secure? And what properties of the hash do we need for that to be secure? So let me tell you a little bit about this paradigm. It was actually developed as a means to convert what we call identification scheme into digital signature scheme. That was where kind of the context in which this paradigm was proposed, even though now it's used widely. And indeed, one of the most widely used signature schemes today is based upon this paradigm. So everyone who's using iPhones or anything, you use Fiat-Shamir paradigm every day, so you use it. And now there's a question, is it secure? And let me tell you, in practice, it's secure. It's a great way to eliminate interaction, to convert identification schemes into signature schemes. It works. But we're scientists. And we want to know, okay, but is it really secure, or just nobody broke it yet? We want a deep understanding. What's going on? Is it a good way? Is it a fundamentally secure way of reducing interaction? And what properties of this hash function do we need in order to argue that it's secure? So here's what we know. If you model this hash function as a truly random function, like a truly, truly random function, which of course our functions are never truly random, but if you think of it as truly random, this is what we call the random oracle model, then it is secure. But now you can ask, okay, and what if it's not a random function, which in real world it isn't? Then turns out we actually have counterexamples. We have examples that show that this paradigm is not secure. So should we worry? And the answer, not really. These counterexamples are very contrived. It's just kind of a means to say, don't try to come up with a general proof that always works, because counterexamples exist. But these counterexamples are very contrived. However, let me tell you something slightly more worrying. The interactive argument that I showed you of Kilian and Mikhaili, the one that hashes the PCP and opens, that exact one actually turns out, if you apply the Fiat-Shamir to that one, there's also some risks, in theory. What do I mean in theory? It was shown that if you use hash functions there exist hash functions that satisfy the properties I showed you, still a bit contrived, and there exist PCPs that satisfies the conditions I told you, but also contrived, that if you use these, again, this breaks. But if you use natural hash functions and natural PCPs, we don't know. So that's the situation. However, so what do we know? The protocol that I showed you in the random oracle model, it's secure. Not in the random oracle model, the truth is we still don't know. However, here's what we do know, which is quite interesting. If you use a hash function that has some additional requirement, it's called somewhere extractable. I don't want to bore you with the definition, but the point is an additional assumption, additional structure that we know how to instantiate under standard assumptions. So this kind of hash that's somewhere extractable by now is bread and butter for cryptographers. Okay, so we know how to do that. But if you also assume that the PCP has additional structure or stronger soundness guarantees, it's what we call non-signaling soundness, then again we get security. So we impose slightly stronger conditions on the hash and the PCP. And then we can get security with a slight different, not exactly the protocol I showed you, slightly different, but nevertheless. And now we should ask, okay, so do we have these primitives? And the somewhere extractable hash function, yes, easy. How about this non-signaling PCP? And what is this non-signaling business? Anyway, so I'm not going to define what it is, but let me tell you, it's a really interesting notion that came actually from quantum physics. Okay, so this is a notion that's studied extensively by quantum physicists. It's quite interesting that it came in this context. What I'm showing you now, I don't care. I'm not being post-quantum secure. No, I don't care about quantum at all. I just want to shrink my proofs. And I'm considering only classical adversaries. I don't even care about quantum. Still, this notion of quantum came up. Turns out that kind of secure kind of cryptography and this quantum thing, somehow there's a very tight connection between them. In particular, also encryption, which you didn't see here quite, even though it's hiding underneath these primitives. But secure encryption and this non-signaling soundness are very closely entangled in some kind of weird coincidence. But now we should ask, do we have such PCPs? And here's what we know. For deterministic languages, so if I want to prove to you that some deterministic computation is correct, very long computation, I want to prove that that's correct using kind of PCP or non-signaling PCP that you can verify efficiently. Yes, we know how to do that. Great. That's was done. How about non-deterministic languages? Okay, this question keeps me up at night, okay? Do we have it for non, like can we just for any proof convert it into a PCP that has a non-signaling soundness? And you know, for a while, we thought the answer was no, because we can prove that the answer is no for some limited, for some parameters of PCP. But recently we noticed that actually there's a very, very interesting parameter regime. Again, I don't have time to say more, but there's some interesting parameter regime in which actually we believe now that it is possible. Now, this is a religious belief. I have no reason to, maybe it's because I'm an optimist. But now we're kind of, you know, spending most of our waking hours trying to prove this. So let me summarize here. So what did we do today? I hope I convinced you of like at least a little bit of the magic in cryptography. Essentially what we showed how to take any long proof and compress it into a succinct certificate. We did it via the beautiful evolution of proofs in computer science, going through interactive proofs, multi-proof interactive proofs, and finally probabilistically checkable proofs. What we did, the first thing we did is use standard cryptography to construct interactive version, an interactive succinct computationally sound proof or argument. And then we showed how one can eliminate this interaction and get a non-interactive solution using cryptography. It's secure if you're willing to rely on what's called the random oracle model, if you assume your hash function is truly random. It's also secure if you assume the existence of non-signaling PCPs, or PCPs with this kind of strong non-signaling soundness, which is inspired from quantum physics. And do we have such non-signaling proofs? Well, for deterministic computations, yes. And for non-deterministic ones, that's kind of still our million-dollar question. I hope that next HLF, I'll be able to say yes. That's kind of my hope for you. But I encourage you all to try to help me. Okay, thank you very much.
Thanks a lot for a great lecture. In the intersection between computer science and mathematics, this is really perfect for HLF. We now are open for some questions. You want to answer? If you're willing to. Let's see, we are open for some questions. There is something in the back.
Yeah.
Wait for the orange box, please.
Oh, wow. They're more polite, you know, they pass, they don't like throw.
Instead of just throwing it back, yeah. Hi, my name is Dominic. I'm actually also a cryptographer. And I had a question regarding the cryptographic assumption. So you said that we could, you using like hardness of factoring of product of two prime numbers, but if we change the underlying cryptographic assumption to something like LWE, can we still do this but make it quantum secure?
Okay, great question. Actually, we don't rely on factorization. I gave that as an example because I assume most of you are familiar with that problem. Our schemes are based on learning with error and LWE or other assumptions. We can make them under like decisional Diffie-Hellman assumptions or other. I just used factoring because I assume most of the audience is familiar with that problem.
Okay.
But actually, we do not know how to make them under factoring. But we do know under post-quantum LWE.
All right, thank you very much.
Thank you. There was another question a little bit in front, in the middle.
Hi, thank you for the talk.
Thank you.
So I was wondering, can you use some property of these certificates to show that some statement is independent of some set of actions or something like that?
Again, if I can construct the certificates to show.
If you can use some property of the certificates to show that something is unprovable, like it's independent.
Oh, something is unprovable?
Yes.
Oh, great question. So, okay, all we know how to do with these certificates is to convert long proofs into short proofs. So, if you have a long proof that something doesn't have a proof, for example, take something in co-NP. So you want to argue that an instance is not in the language. There's a proof for that. Go over all possible witnesses and see that each one of them is not in the language. This proof will be exponential. What we can show, you can take this exponential proof and compress it to be polynomial. And now this polynomial proof is going to be a proof that X is not in the language. In other words, that it doesn't have a proof. So the answer is yes.
Thank you.
Okay, yeah.
Be careful,
It's
someone's going to
coming.
throw something at you.
Just wait on it.
Thank you.
What
I'm Vince
respect?
Cerf.
They didn't even throw, the thing at you.
So I wear hearing aids and I'm hearing impaired, and what I thought you said at the beginning was that you could take a wrong proof and you could compress it into a good proof.
No, I may have said that, but that's not what I meant to say. What I meant to say is you can take a long proof and compress it.
No, I know that.
Okay.
But first I wanted to make the word pun, because wrong sounds like long.
Yeah.
Okay, so you take a wrong proof and turn it into a shorter one. The real question, though, is whether a wrong proof, if you put it through this process, could be discovered to be wrong more easily.
Good question. Great question. The answer is yes. No, it's really interesting. Actually, I haven't thought about this. You're saying this kind of thing can be used as a program checker or a proof checker. 100%. No, the answer is yes. You take and the thing is, you take a wrong proof, you put it in this process. Even if this process is wrong, it won't verify. Like that, the only way to generate something that verifies is actually by breaking my cryptographic assumption. So I can actually reduce, I can take someone who manages to break, like to generate false or accepting proofs for false statement, and I can use them to actually break my assumptions, which that we believe really you cannot do. So you are right that you can do that. However, let me say one thing. If the process of converting a proof to the PCP, if that process is faulty, then even if the original proof was correct, you'll end up with something faulty. But assuming that transformation that takes you from a proof to a PCP is not faulty, like that thing can be done in a way that we believe, like it should be, then what you're saying is completely right. It can be an efficient kind of proof checker. And actually, that's kind of the point of this, right? That you can efficiently, because now we write proofs. I have papers, 150-page proof. Nobody can verify. I can write whatever I want. Actually, I can claim whatever I want. Nobody's able, which human can read or wants to read 150-page proof? So that's the point of this. This is to make it efficiently verifying, to catch mistakes. Thank you.
Okay, I think in the interest of time, we stop the discussion now, and thank you, Yael, for a great lecture.
Thank you.